Okay, but now what we're going to do today is before we get started, we're going to review a net ionic equation. So pull out the handout that you guys picked up from the Chrome cart. And what we're going to do is we're just going to go through precipitation reactions again. So there's an example up there to refer back to. We're not going to do the entire handout together. We're just going to be doing numbers 2, 3, and 4. And again, if at any point you feel confident doing this on your own, you can kind of go ahead and finish it up just because I want to make sure you guys have some practice if you guys don't need me. But if not, totally cool. I'm going to go through it step by step, okay? All right, so our first reaction, our reactants are sodium sulfate and silver nitrate, okay? So what we want to do is we want to do that double replacement reaction. And so what we're going to do is we're going to switch the two ions with each other. But before we do that, let's just kind of figure out what they do in solution. Wow, I always forget there's announcements. Sorry, guys. Alrighty, guys, sorry about that. So some of you guys, it looks like are already working on it. But let me just, again, go through it. Just make sure we're all on the same page for this problem. So before we go with the double replacement, let's just kind of figure out what they break apart to inside of solution. So if Na2SO4 is aqueous, what that means is that all of the ions inside of that molecule are just going to be dissolved in water. So even though the compound is Na2SO4, it's going to exist in water as separate ions. Okay, so they're going to be ionized. And so they're just going to be floating around inside the water in their individual molecules. Because remember, we talked about the first day of the Unit 4 lesson that water, it has a partial positive and a partial negative, right? And so the partial positive is going to attach to the negative sulfate, and the partial positive is going to attach to the positive sodiums. And so that's how it's going to break down the ionic compound. And that's what aqueous means. It just means that they exist in water, but they're broken apart into their individual ions. So Na2SO4 is going to break apart into two individual NAs and an SO4 2- inside of solution, okay? Okay, so what about AgNO3, okay? What's the charge on Ag gonna be? 1, yeah, +1, because again, this one you have to memorize. Nitrate, NO3 is always gonna be minus, and since there's only one of them to balance it out, it's going to just be +1, okay? All right. Now we're going to do that double replacement action. So what we're going to do is we're going to get the positive cation from this compound, and it's going to check out the negative anion from the other compound. So Na and NO3 are going to be like, oh, that person looks, or that ion looks kind of good looking. So they're going to try to hang out. Okay, but what we're going to do is we're going to use our solubility rules to figure out if this is going to make a solid, a precipitate, or if it's going to stay aqueous. So hopefully you guys remember, what did we say about sodium and nitrate? They're always what? They're always going to be single. They're always going to be soluble, right? And this is actually both of the rules you had to memorize. Anybody in group 1, right? Group 1 of the periodic table, they're always going to be soluble. And nitrate is also always going to be soluble. So unfortunately, even though they were initially attracted to one another, they are not gonna make a precipitate. They're not gonna make a solid, okay? They're just gonna check each other out and then kind of go back to doing their own thing. All right? And again, if you're confused why this happens, refer back to the workbook and the 2 solubility rules you had to memorize. Group 1 compound ions will always be soluble, and nitrate is always soluble. Oh, excuse me. All right, now we're going to double replacement the other one. So we got sulfate and we got silver. So we're going to combine them together. But how many silver ions will I need to balance out the -2 charge on sulfate? 2. So that means I'm going to have Ag2SO4. And again, it's because if you notice, sulfate is 2-, silver here is +1, which means that you'll need 2 of them to balance it out. Okay, which means in order to balance this equation, you would have to put a 2 in front of here and a 2 in front of here. That way everything is balanced out. Okay, looking at your solubility rules, is Ag2SO4 going to be soluble or insoluble? Okay, let's go back to, let's take a look at the solubility rules, guys. Ag2SO4. Okay, so if you guys take a look here, we're going to look at SO42 minus sulfate, and it says that it's always going to be what? Soluble. And the exceptions are strontium, barium, mercury, and lead. Do we see silver 1 on here? No. So is it going to be soluble or insoluble? Yeah. So in this situation, our silver sulfate is going to be soluble. In reality, it is soluble, but only a little bit. But for the purposes of the rules that we learned, just know that silver 2 nitrate or silver 1 sulfate is going to be aqueous. Okay, so if we mix these guys in a container, are we going to form any precipitate? No, that means if we have a container and we mix these two solutions, we're just going to have a bunch of sodium ions floating around. We're going to have a bunch of nitrate ions floating around, a bunch of silver 1 ions floating around, and a bunch of sulfate ions floating around. Nobody's going to form any solids. So there's going to be no precipitate. Okay, so unfortunately, in this group date, there was no chemistry. Nobody got together with anybody. Okay. All right, so if we were going to try to write the net ionic equation, okay, we can't. There is no net ionic equation. Okay, because nothing happened. They didn't form any solids. Everybody started dissolved in water, and then everybody ended dissolved in water. Nothing happened. They're basically just doing the same thing. Yeah, what's up?
So on a test, gets like this, NIE, or do you have to say
For the AP test, since we are prepping for the AP test, get used to writing no net ionic equation, because the grader might see no NIE and be like, what are they talking about? They'll probably know, but better safe than sorry, right? Yeah.
So there's a two silver nitrate.
Yeah.
We have to do double the drawing.
For this handout, no. Okay, any questions? Hopefully this kind of helps you guys visualize a little better. I picked this handout because they have these little pictures so that you guys can see it. We'll do one more question. We'll do number 3, and then we'll go on to our regularly programmed scheduled programming or whatever. Okay, we'll do number 3. So take a second or take about 2 minutes. You can work with the person around you. I want you guys to fill out the drawings, right? Figure out what the ions are, and then try finding the net ionic equation afterwards. After that, we'll move on to the regular classwork stuff. I'm sorry, I don't have any work for you. You can just relax today. Thank you, though. It's because you guys work so hard. There's nothing left. All right, you guys, I'll give you another minute to finish that one up. Alrighty, guys. If you guys are finishing up, feel free to do so while I'm finishing or I'm going over this. But if not, let's make sure we got the correct answer, okay? Okay, so we have calcium chloride as the first compound. This is going to break down in water, or it's going to exist in water as Ca2+, and there's going to be 2 Cl minuses. Hopefully everybody got that for the original drawing, right? CaCl2, if it's aqueous, it's going to exist in these ions inside of water. Okay, and then for potassium carbonate, we're going to have 2 K+ ions, and we're going to have 1 CO3 2- ion. And again, this is what aqueous means. It means it's dissolved in water. And so for ionic compounds, they're going to exist in the separated ions. Okay. All right. Now what we're going to do is we're going to do that double replacement action. So calcium is the cation in this one, and then carbonate is the anion in this one. So they're going to kind of check each other out. And what's going to happen is it takes 1 calcium and 1 carbonate to balance out the electronic charges. So for this one right here, is this going to be a precipitate solid, or is it going to stay aqueous? Yeah, this one is going to be a solid. Okay, and again, if we go back to our solubility rules for carbonate, oops, this is the wrong part. Why are we all the way down there? So if we go down there for carbonate, if we look at carbonate's going to be insoluble unless it's bonded to NH4+ or the group 1 cations. And obviously calcium is not. Calcium is a group 2 cation. And so that's why calcium carbonate is going to form a solid. So if we mix these 2 solutions together, what's going to happen is on the bottom, we're going to get a solid, a precipitate, and that's going to be calcium carbonate, okay? And so that's what a precipitate is. Okay, so if you mix these 2 solutions, both of them are probably going to look clear, or they're going to be homogeneous. It's just going to look like a liquid with nothing dissolved in it. But when you mix them together, you're going to form this precipitate. Okay. All right. Then we're going to do the double replacement for the other side. So we have potassium and we have chlorine. That'll make KCl. And we're going to have to balance this out by putting a 2 in the front of it. And then for this one, is this going to be aqueous or is it going to form a solid? Yeah, this one is going to become aqueous. Why though? Yeah, potassium is in group 1, right? Since potassium is in the first column or group 1, nobody wants to be with potassium. Potassium is just not really attractive to anybody. Everyone just wants to break up with it, unfortunately. And so potassium chloride is going to exist like this. Okay, so this is basically what happens. You mix these 2 aqueous solutions together, and what's going to happen is the calcium carbonate is going to form a solid on the bottom, but the potassium and the chlorine are going to stay floating around as ions inside of the solution. Okay, what's up? No, this would be pretty much exactly what happens. It won't sink to the bottom like this, like all of a sudden. You don't get like an instant like solid formation on the bottom. Usually you'll see like it'll start getting cloudy, and then you'll see like little like foggy parts, and that'll eventually settle to the bottom. Those are the solid precipitates. Alrighty, so that's all the review we're gonna do for actually we need to write the net ionic equation. Sorry about that, guys. Okay, but if we're good, I'm gonna erase the first initial pictures, and then what we're gonna do is we're gonna write the net ionic equation. I have one thing I do want to go over on this problem afterwards, and then we'll move on to the class. Okay, let's write the net ionic equation. Okay, so for the reactants, what's the first reactant that we should write down for the net ionic equation? Yeah, calcium, right? For the net ionic equation, we only want to write down the ions that did something. And so calcium and carbonate formed the solid. And so the first ion that we care about is calcium. Now, what's the charge on calcium? 2+. And what should we put for the state of matter notation? Aqueous, yeah. Aqueous, aqueous, potato, potato, same thing, right? All right. All right, and then we're going to add that to, what's the other ion that we should write for the reactant? yeah, carbonate CO3, and the charge is going to be 2 minus. And what's the state of matter for this guy? Aqueous, good. And then that's going to form calcium carbonate, and that's the solid, okay? So that's going to be your net ionic equation. Now, there is one more thing I did want to go over. I forgot to go over at the end of class last time, and it's called a spectator ion. Okay? And spectator ions are basically what the name suggests. They're spectators. They just kind of watch. They don't do anything, right? Just like how when you go to a sporting game, the people that do something are the athletes. I guess these guys are the athletes because they did something. But the spectators just kind of chill and like look around and see what everyone's doing. So just based on the name, what do you think the spectator ions in this reaction were? Exactly, potassium and chlorine. Okay, because all they did was kind of switch around, but they didn't really change. They stayed aqueous, so they're just spectating. They're just kind of looking at what happened. Okay. So that's the net ionic equation. That's the spectator ion. And this amazing handout was given to us courtesy of Mr. Pepic. So can we give Mr. Pepic a hand? I told you guys, he's just a better, taller, smarter version of me.
Every handout I've gotten up to this point this year has been from him. And not once have I said to my students,
Wow. So
I got
humble.
that from somebody else.
Look at that humility.
But now I need to go back and say, you know what? I've been stealing. Been taking
It's not
from the
stealing.
best chemistry teacher in the school.
Yourself?
No, I don't steal from myself.
Alrighty, guys. So any questions about this part right here? Net ionic equation, spectator ions. Oh, according to Mr. Pepic, the ones that react, they're called reactant species. So make sure you guys write this down.
That's the terminology.
See, and then he says that I'm the best teacher. Obviously not. I'm
Because
sorry,
I know,
guys.
because I know one little
I'm sorry,
tidbit of
guys. You
information.
guys got shortchanged with me.
No. Just so you know, when I have a question, I go to him.
Hey,
No,
all I know is that you're taller than me, and that's all that matters in life.
And you can jump higher than I can. So
See, but
me being
I'm in my physical prime.
Yeah.
You're long past your physical
you hear what he
prime.
just said? I'm past my
You are
peak.
long past your prime.
And I'm out of here, ladies and gentlemen. I got my hints, Mr. O.
Yeah, so those are called reactant species. Sorry about that. I should have mentioned that as well. Okay, so reactant species are the things that react, and spectator ions are just the guys that watch and don't do anything, okay? Alrighty, so with that being said, let's pull up the class workbook, number 4. We're gonna be picking up where we left off at section 4 called acids, bases, and neutralization reactions, okay? So I'm gonna leave this up here for just another second, but we're gonna be picking up right here. Section 4 is called acids, bases, and neutralization reactions. All right. So what we're going to talk about now are obviously acids and bases. I'm sure you guys have heard those words before if you guys took any science class before. Acids and bases are pretty important. Okay, but we're going to give them a proper definition here before we talk about them. But don't freak out too much because the way they react, they're called neutralization reactions, and they're basically what we just did. It's just we're looking at the ions and seeing what they form, okay? So let's start with acids. Okay, acids, they're substances that ionize in aqueous solution to form H+. Okay, so basically an easy way to say that is when you put them in water, they break down into H+ and something else. Okay, that's pretty much it. Okay, there are other definitions of acids that you'll see when you guys read your textbook, but the definition that we'll be going on, or that we'll be using for this unit is going to be proton donors. They form H+ when you put them in water. Okay, again, there are other definitions for acids, other ways to define them, and you guys can read that in your book. But for the purposes of this unit, we just need to know that they donate H+. Okay. All right. So with acids, there are different types of acids. Okay, the first type of acid we're going to talk about are monoprotic. Okay, mono means one. Okay, so mono is the prefix that means one, and so they release one H plus. Okay, so this right here, HCl, is an example of a monoprotic acid because it only has one H plus, one proton to give away. Okay. Another type would be a diprotic acid. Di means two, and so they can release two H pluses, right? The naming is so creative, isn't it? Okay, monoprotic releases one H plus. Diprotic can release two. And so an example of a diprotic would be H2SO4 because it has two H's. Now, it does it in steps. So it can release one H plus, and then it'll form a monoprotic acid, HSO4 minus, which can also release an H plus. Okay. This doesn't happen very readily, especially the second step does not happen very well. We'll talk about that later in the year, but just know that monoprotic means it can release one H plus, diprotic means that it has a potential to release two. Okay. Any questions about monoprotic, diprotic acids? Pretty self-explanatory, right? All right, so that's acids. Just consider them H plus or proton donors. They just give protons in the aqueous solution that they're in. Okay, the other half of that are bases, and bases are we'll think of them as the opposite of acids. Again, there are different ways to define acids and bases, but we're going to define it as the opposite of acids here. So acids give H plus, bases accept or react with H plus. So they take H plus. Okay, so easy way to think about it is acids, they give H plus, but then bases, they take H plus. Okay, they take H plus from their aqueous solution. Okay, easy way to recognize bases is that they produce OH minus ions. They produce Me, hydroxide. Okay, so an example would be right here. Lithium hydroxide breaks up into Li plus and it releases OH minus. Okay, so we can think of bases as things that take H plus or they give OH minus. Okay, so whenever you think about a base, think about Me. Mm-hmm. It's all about that base. Okay, so we said that bases give OH minus, but not all the time. There are compounds that do not contain OH minus that can also be bases. One example is ammonia, NH3. NH3, if you notice, NH3 does not contain OH minus. However, it can accept an H plus and form NH4 plus. Okay, so if you guys notice, in this reaction, what happened was it gained H plus. And so ammonia, NH3, is considered a base even though it doesn't have OH minus, okay? So that's why we like to use we're gonna use two definitions in this unit. Again, if you wanna look at the definitions more carefully, it does outline it very detailed in your book. So just make sure you guys check that out. But for this unit, just make sure you guys know that acids give H plus, bases take H plus, or give OH minus. Okay. Any questions about the difference between acids and bases? No? Okay. All right, so with that being said, we do need to talk about something else about acids and bases. Remember how we talked about strong electrolytes and weak electrolytes, right? Strong electrolytes, almost everything dissolves in water into the ions, and in weak electrolytes, not everything breaks down into ions. The same thing is true with acids and bases. There are things called strong acids and strong bases, okay? Okay, sorry, let me, yeah, so a strong acid breaks down completely in water. So we have 7 strong acids, and you do need to memorize these, okay? I know, I'm so sorry. You have to memorize the strong acids. Okay, but if you look on the periodic table, Cl, Br, I, they're on the same column, so it's kind of easy to memorize. It's in the second to last column. They kind of just go down. Cl, Br, I. You also need to memorize the 4 down here: chloric, perchloric, nitric, and sulfuric. Basically, what this means is that if you put any of these strong acids, sometimes they note it like this, HX. When you put them in water, they will completely break down into the positive ion and the negative ion. Okay, it's going to be almost 100% ionization. Okay, so almost every single one of these molecules, these acid molecules, will break down into H plus and whatever the anion was. So if you put HCl in water, it'll break down almost 100% into H plus Cl minus. If you put nitric acid inside of water, it will almost completely break down into H plus and NO3 minus. That's basically what it is. It just that's what it means by strong. Okay, it's not about what it can move or what it does. It just breaks down completely into its ions. What's up?
Why does like acid, like let's say acid, like melt everything?
So not everything. Usually what we equate it with is with like living things and metals, right? Basically, when acids release H plus, it's gonna react with the metal or whatever your organic matter is, because you're mostly made of water, so it reacts with the water inside your cells, and that's what causes it to melt through. We'll talk more in detail about this, and we'll be working with a couple of acids in some of our labs. So you'll see why on a more technical level later. But just know it's the H plus that reacts with the water usually, or the metal. Okay, so these are strong acids. Okay, in contrast, weak acids, they don't completely break down. So an example of a weak acid would be HF. Okay, and HF does break down into H plus and F minus, but not 100%. So we use this arrow right here. You see how it goes in both directions? We use this arrow to represent that it's a weak acid. It doesn't completely turn into H plus and F minus. Okay. So if I had an aqueous solution of HF, I would have some H ions, I would have some F minus ions, but I would also have a bunch of HF molecules still floating around. In contrast, if we have a strong acid like HCl, I would just have H plus and Cl minus in there. There's no HCl in there, okay? Because everything breaks down. There's no HCl. And that's the difference between a strong and a weak acid. Yeah, but these ones are a lot easier. I'll show you guys why. Yeah.
Never mind. I was just gonna say that strong acids are always weak bases and weak bases.
Yes, we will talk about that later in the year. Yeah, what's up, Great? Which part? Ionization. It means it turns completely into ions. Okay. Yeah. Yeah, this means that it doesn't break down completely. Like you see how this arrow goes only one direction? So saying everything's gonna go that way, but this back and forth arrow means that it's not gonna go completely that way. It can go the other way too constantly. Yeah. Okay, so those are strong acids and you have to memorize them. You also need to memorize the strong bases. But bases I think are a little bit easier. Just look at the first column and the second column. Okay, so all the strong bases are in the first column and the second column. LiOH, NaOH, KOH, RbOH, CSOH, and then we have calcium hydroxide, strontium hydroxide, and barium hydroxide. So bases, a lot easier to remember just because they're in the first two columns. Okay, and strong bases are basically the same thing in terms of what they do. If you put a strong base inside of water, so for example, if we put LiOH inside of water, it will almost 100% turn into Li plus and OH minus. Okay, that's a strong acid. But if you have a weak acid, okay, for example, I don't know, like aluminum hydroxide, okay, it's only gonna turn partially into Al3 plus and partially into OH minus. Okay, remember the back and forth arrow. So strong strong bases, sorry, will turn completely into its ions. Weak bases do not turn into all their ions completely. Yeah, what's that? No, these are just the strong acids, strong bases. Just memorize these as the ones that go 100% into their ions. Any other acid and base you see does not go 100% into their ions. So yeah, the exceptions will be everybody that's not mentioned here. Okay, good question. All right, any other questions about strong acids, strong bases? Yeah.
Example of like a base, but no like vinegar and acid.
Vinegar is an acid, yes. Ammonia, the stuff in your Clorox would be an example of a base. Bases are a little bit trickier. Water can be an acid or base. Yeah. Yes, it is the middle. Okay, so with that being said, we're going to start looking at the reactions for this part. So when an acid, acids and bases are kind of opposites of each other. So when you mix an acid and a base, we call that a very special type of reaction. It's called a neutralization reaction. Okay, when you mix an acid and a base, we call that a neutralization reaction because they neutralize each other. They kind of get rid of one another. Okay, and in a neutralization reaction, it always produces water and a salt. And by salt, we just mean an ionic compound. Okay. And the ionic compound will depend on whatever the anion from the acid was and the cation from the base was. So here we have an example. So this is what I mean by, this is the same thing that we did with the ionic equations. Okay, we have a strong acid, HCl, and a strong base, NaOH. And they basically did the old switcheroo, right? They went on a group date, and then H and OH combined, right? HOH is the same thing as H2O. And so they make water, which is, as we know, a liquid. But then chlorine and sodium, the other cation and anion, they're going to form a salt, which is NaCl. And salt just means an ionic compound. Okay. And so that's what we call a neutralization reaction. It's just a specific type of ionic equation. What's up?
So people who have like trouble from acid reflux and
Yeah, and acids. Yeah, it neutralizes it in their stomach. Yeah.
would that increase their sodium levels?
Yes, it would. If usually we don't take like a sodium antacids, but yeah, it would increase the salt concentration in your stomach. That's how a lot of older antacids work. Like if you in your stomach, if you have a lot of acid, what they do is they take some sort of base, and then basically the acid just turns into water and the salt. And so yeah, it would increase your salt concentration, but not to the point where it's like, you know, going to cause hypertension or whatever. Yeah. Good question. All right, so let's do an example. I think that's the best way to kind of see how this works. So we'll do one together and I'll let you guys try one on your own. Okay, so we have HCl, okay, and we have CaOH2. Okay, let's first identify, let's do part B first. Let's figure out which one's the acid, which one's the base, and if they're strong or weak. Okay, so let's look at HCl. Is HCl gonna be an acid or a base? Acid, yeah. Hopefully you guys should memorize this soon. Okay, this one is an acid. And is it gonna be a strong acid or a weak acid? Strong, yeah, it's on the list. So it's a strong acid. Okay, not much to say there. Okay, we'll look at calcium hydroxide now. Okay, so if this is a acid, then this is obviously gonna be a base. It's gonna be a strong base because it's on the list. Okay, so we got a strong acid and a strong base, which means they're gonna completely ionize. And so let's do the switcheroo, okay? They're gonna go on a double date. And so HCl, the H is gonna be like, hey, I don't like Cl too much. Cl kind of talks a little too much, a little too acidic for me, a little too toxic. So it's gonna hang out with the other anion. So if we have H and OH, what compound is that gonna form? Yeah, so we can write HOH, but if you notice there's two H's and an O, so that's basically the same thing as H2O. Okay, And H2O, what's the state of matter? Yeah, liquid. So H and OH are going to form H2O. Okay, and then Ca and Cl are going to be like, oh, we got ditched. And so now we need to hang out with the other person. And so they're going to form CaCl2. Now for CaCl2, is this going to form a precipitate, or is it going to form an aqueous compound? It's going to be soluble. Okay, so look back at your solubility rules. Look at CaCl2, guys. Is this going to form a solid, or is it going to stay aqueous? Yeah, aqueous. If you look at Cl is always going to be soluble unless it bonds with silver, mercury, or lead. So CaCl2 is going to be aqueous. So unfortunately, they're going to break up. Okay. Oh, and then obviously, I forgot to put aqueous for both of these. Sorry about that. Okay, so this is how we write the equation. So this is going to be, we said last time, the molecular equation. Okay, let's write the net ionic equation now. Oh yeah, we do need to balance it. Good call. Sorry guys, it's been a long weekend. Okay, so to balance it, we just need to put a 2 in front of the HCl, and then we're balanced. And water. Thank you. Okay, so you've seen a 2 in front of the HCl and a 2 in front of the water to balance it out. Okay, now let's do the net ionic equation, and we're just going to write down the ones that do something. Okay? Okay, so what's the first ion that does something in this reaction? So it has to form water, right? Water is the thing that's formed. And so what are the things that make the water? Yeah, so hydrogen, and what's the charge on hydrogen? Plus, so that's going to be aqueous. And then obviously we're going to have the hydroxide, which is negative. And so this would be the net ionic equation. Okay? And that's it, guys. We got the molecular equation and the net ionic equation. And again, this is called a neutralization reaction because the acid and the base, they canceled each other out. Okay? Any questions about that? Yeah.
So then I have an equation that's not basic.
Yeah, so anything that actually ends up changing, because if you look at the reactant side, the Cl and the Ca, they started aqueous, and then on the right side, they ended up aqueous. So they didn't really do anything. They're just floating around still. And so they're not part of the net ionic equation. Okay. Alrighty, so if you guys don't have any more questions on that, let's go to 4.9 and try that out. If you guys want to take about 2 minutes, try writing the molecular and the net ionic equation for 4.9. And then after that, we'll move on to the last topic for today, which is probably my least favorite part of the entire unit. You'll see. Yeah, go ahead. Okay, so take about 2 minutes, work on 4.9. You're going to write the molecular and the net ionic equations. Okay, and I'll leave this up here just so you guys can look at it to see what we're looking for. Oh, I'm so sorry, guys. I made a little typo on 4.9. It's supposed to be solid, MgOH2 and aqueous. Okay, so it should be this. Solid MgOH2 and aqueous HBO. So it changes things a little for the net ionic, but the regular reaction is the same. Sorry about that, guys. Oh, you can just throw it in the box. Thanks. Yeah, the net ionic's a little weird on this one. All right, I'll give you guys another minute and then we'll go over it together. I think you eat more noodles than I do.
A lot of ramen. What's ramen?
I'm all right.
It's spicy. Got a little kick to
It's not
some egg
spicy
finish.
to me though.
Trust me. You can have it
Mr.
more spicy.
Pepe, Koreans have the #1 rate of stomach cancer for a reason.
Really?
Yeah, we do. It's because we
All the Koreans in here just went, oh
Yeah.
crap.
it's because we eat the most spicy and the most fermented food. Yeah, it really is. Yeah.
What does it mean fermented food, Mr. O?
Basically, we put it in a pot and then we put it in the ground for a long time so the bacteria can grow in there and so it lasts longer. Huh? Yeah. So it is healthy because there's like good gut, it forms good gut flora, but like, yo, the smell from Korean food sometimes, yeah, it's pretty rancid as a
Do you
Korean.
think it's causal?
Huh?
Is it directly proportional?
To what?
The food you eat, the stomach cancer?
I think so.
You don't know if it's from that. Form
Yeah.
fermented
This
food?
is based on my, I don't know if you can tell, but I'm not that smart of a guy. This is based on my YouTube, Wikipedia conspiracy theory, why Koreans have the highest rate of stomach cancer.
I won't argue with that.
Yeah, I need to write a narrative for myself, right?
Maybe they're mixing the North Koreans in this.
No, because they don't eat. Alrighty, guys. If you're still finishing up, feel free to. Maybe this part probably shouldn't go on YouTube, but let's go over 4.9 and then we'll get started. Okay. So
You know what?
let's first.
Really, you might want to go.
I might want to. That North Koreans don't eat.
Just, yeah. That you might want to.
Man,
Think about that.
it's politically incorrect to say the truth now. Anyway, all right. Let's go over MgOH2 and aqueous Br. So start with MgOH2. Is this a solid or is this an acid or a base? Yeah, this one's a base. And is it a strong base or yeah, strong base? Okay. Hopefully this kind of helps you guys as you memorize it. We got a strong base. And then HBr this is obviously an acid, strong or weak acid. Strong, yeah, strong acid. Okay, so let's start off by writing the molecular equation, okay? Because that's the one that's easier and the one that we're more familiar with, okay? So we're gonna start with the two reactants. We're gonna start by writing MgOH2, and that's gonna be a solid, so just make sure you write the state of matter notation. And then we're gonna react that with HBr. Okay, which is going to be aqueous. Okay, now we're going to do our double replacement switcheroo. So magnesium is going to react with what? Yeah, bromine. And how many bromines will I need to balance out the magnesium? 2. Okay, so if you guys take a look at this, is this going to be a solid or is it going to be aqueous? Yeah, magnesium bromide is going to be aqueous. Okay. We're gonna, and then it's also gonna form water, right? H2O, because H and OH. And obviously we know that water is gonna be a liquid. Okay, we also need to balance out this equation. So for the balancing, you should just put a 2 in front of HBr and a 2 in front of the water. Okay, hopefully everybody got that for their molecular equation. All right, so here the net ionic equation is going to be a little bit different because our base started off as a solid, right? Okay, so we're gonna have, it's not gonna be the same as the previous net ionic equation. So if we take a look at MgOH2, did this thing end up changing? Yes, it changed. God bless you. Because it started off as a solid, and then the magnesium became aqueous, and then the hydroxide became liquid, right? Because if you guys see, magnesium turned into what? Aqueous, and then the hydroxide turned into water, which is a liquid. And so we need to include MgOH2 solid in the net ionic equation because it went from a solid, and then the magnesium became aqueous, and then the hydroxide became a liquid. Okay? So for the net ionic equation, we need to include everybody that changed states of matter. Okay? All right, let's move on to HBr now. Okay? Were there any ions in HBr that changed state of matter? Okay, let's look at hydrogen. Where did the hydrogen go in the products? Yeah, the hydrogen went to water. So hydrogen went from aqueous to liquid. So should we include hydrogen in the net ionic? Yeah, we should include hydrogen. Okay, so we're gonna write H plus aqueous. Okay, but what about the bromine? Did the bromine change state of matter? No, right? Because bromine was aqueous. It was just kind of floating around, and it's still just kind of floating around because it stayed aqueous. So we're not going to include bromine in the net ionic equation. Okay, does that make sense? All right, now we're going to take a look at the products. We said earlier the magnesium did change state of matter, so we're going to write Mg, but now it's aqueous, so we need to write Mg2 plus aqueous. Okay, and again, if it's aqueous, it means it's floating around as an ion inside the solution, so it stays like this. We said bromine didn't change, it's just aqueous still, so we're just going to leave that one out. And then lastly, we have the H2O, which is a liquid. Okay. All right, and then we also need to just end up balancing, which is going to be the same thing as before. We put a 2 in front of the H plus and a 2 in front of the H2O. And there you go. That's your molecular equation and the net ionic equation. So I know this one was a little bit trickier just because it started with a solid base, but just make sure you guys keep that in mind as you guys are writing your net ionic equations, okay? Everything that changes state of matter will be included in the net ionic equation, okay?
That's a good lead into redox.
Yes,
It's a really good equation.
I appreciate that. Just stealing from you.
So nothing. Just my partner.
Oh, thank you. That's exactly what I wanted to do. Alrighty, guys. So we're gonna go into the next section, oxidation reduction, but I'm gonna give you guys just a 5-minute break, just to kind of relax, get some air if you need to, and then after that, we'll go into the last section for today. Okay, so take a little break. All right, yeah. So for this part, it's called oxidation reduction. It's not too difficult. The math is literally just adding and subtracting simple numbers, but there are a lot of rules to remember. So I highly recommend when we're doing practice problems for this section that you keep your screen right here on these rules so that you guys can always refer back to them, and then I'll have the problems up here, okay? So just because you haven't memorized these set, it's your first time encountering it, have this part, this screen, once we get here, the oxidation number section, these rules on your screen, so that when we do the problems, you can constantly just look at the rules and the problems will be up here for you. And if you can't see anything, let me know and I can always zoom in, okay? Okay, but let's talk about oxidation reduction reactions. Okay, so this section is going to be talking about special types of chemical reactions called oxidation reduction. The short way of saying it is redox. Again, chemists are really lazy. We don't want to say the whole word, so we just take re and ox, or read and ox. So redox reactions. Exactly. And then so in redox reactions, what we are looking at is how the electrons are transferred from one reactant to another. Okay, so we haven't talked too in detail about these yet, but when chemicals react with one another, the electrons are the things that move around, and that's what allows them to react. And so in redox reactions, what we're going to be doing is we're going to be looking at how the electrons move around from one reaction to another. Okay, so in terms of redox reactions real life, you guys are probably all familiar with corrosion or rusting, right? When metals, a nice shiny piece of metal, it kind of gets weathered down, it gets wet, it starts to rust into that nasty feeling thing that gives you tetanus, right? That's an example of a redox reaction. Okay, and so in rusting, what happens is the metal, it loses electrons and it forms a cation. Okay, right? Because electrons are negative. If you lose something negative, you become positive. So in rusting, we have a metal. It's going to lose an electron and it's going to become a positively charged metal. Okay, it loses electrons. Okay, and it's going to give the electrons to whatever it's reacting with, which becomes an anion, and they're going to form an ionic compound. Okay, so that's just one example of a redox reaction. And we'll be looking at a couple later on, or just in a few minutes. But before we do that, let's talk about what oxidation reduction means. Okay, so I like to use this little acronym right here, oil rig. Oxidation is loss. So if whatever is oxidized, it loses electrons, and reduction is gain. Whatever is reduced gains electrons. Okay. So oxidation is loss. Oxidation is the thing that loses electrons, and reduction is whatever gains electrons. Okay, make sure you guys have this written down because this will be helpful as we go on. And you will have to memorize the difference between oxidation and reduction. Okay, there's not going to be like a cheat sheet on your test or on the AP test for oxidation reduction. So you have to know the difference between the two. Another thing to remember is that oxidation and reduction, it doesn't just happen by themselves. They're like two sides of the same coin. If you have something oxidized, something has to be reduced. Okay, so here we have an example of an oxidation reduction reaction. And so what happens here is the calcium is going to be oxidized. Okay, so calcium is going to be oxidized. Okay, oxidized means it loses electrons. So calcium is basically going to give electrons to the O2. So it gives electrons. And so calcium is oxidized. And since O2 is gaining electrons, that means the oxygen is going to be reduced. Okay, so just keep that in mind. You have to have both together. Whatever gives electrons, whatever loses electrons is going to be oxidized, and whatever gains electrons is going to be reduced. Okay, so that's kind of going to be the basis of oxidation reduction. Now we're going to look at a couple of rules that allows us to see, hey, which reactant is being oxidized and which one is being reduced. Any questions so far? I know this is kind of weird. So again, just keep in mind oil rig. Oxidation is loss, reduction is gain. Alrighty guys, let's now take a look at how we can tell if something is oxidized or reduced. Now, in order to figure out if something is oxidized or reduced, we need to look at something called an oxidation number. It's just a way of us keeping track of whether it gains electrons or loses electrons, okay? So we've talked about how atoms can have charges, right? They become positive, they become negative. Now, oxidation numbers is not that, okay? We're still gonna use positive numbers and negative numbers, but it doesn't always have to do with their ionic charge. So just make sure you guys keep that in mind. Okay, and these rules, you'll just have to memorize them, unfortunately, but it does kind of come easier if we do problems. So let's go through the rules together, and then we'll jump into some problems, okay? So any atom that's in its elemental form has an oxidation number of 0, okay? Elemental form is kind of like, it sounds like a video game thing, but it's basically how it's found naturally, okay? So every element, the way, if it's found, we're talking about its elemental form, we're talking about how it's found naturally. So hydrogen, right? Hydrogen is usually found as H2 gas. And so if we have H2, both of the hydrogen in there have an oxidation number of 0. Okay, phosphorus is found as P4, and so it'll have an oxidation number of 0. And then solid calcium will have an oxidation number of 0. Okay. Okay. The second rule that you guys need to keep in mind is any monatomic ion has an oxidation number equal to its ionic charge, which means if I have an ion that's just one atom, so not polyatomics, okay? So things like K plus, in K plus, K has an oxidation number of +1. Okay, if we have S2 minus, S has an oxidation number of -2. Okay, if we have Al3 plus, aluminum has an oxidation number of +3. Okay, this does not apply to polyatomic ions. You can't say, hey, PO4 has 3 minus, so this is 3 minus. Okay, that's not going to work with polyatomic ions, only for monatomic ions. Okay, I know this is kind of weird. And it might not make too much sense, but once we start using these in problems, it'll be a little bit better. Okay, so the next rule right here, there's one rule, but there's a lot of little like details that need to be said. So just bear with me. But if you guys take a look at this, the rule says that nonmetals, they usually have negative oxidation numbers. Okay, so things on the right side of the periodic table, they usually have negative oxidation numbers. Okay, so this rule is kind of annoying because it says they're usually negative, but they can be positive. Okay, the key thing one of the more important ones to remember is this one. Oxygen usually has a number of -2. Okay, so make sure you guys write that down somewhere, star it, whatever you need to. Oxygen usually has an oxidation number of -2. Okay. The major exception is peroxides. Peroxides are the ion O2 2-, and in there, oxygen has an oxidation of -1, but we rarely look at peroxides. And so for the most part, just know that oxygen is -2 in terms of its oxidation number. Okay, but do keep in mind that if you see peroxide, it's not going to be -2. It's going to be -1. Okay. Okay, hydrogen usually has an oxidation of +1. Okay, when it's bonded to nonmetal. So hydrogen is weird because when it's with a nonmetal, it's +1, but when it's with a metal, it's -1. Okay, so for example, if we have NaH, right? Na is a metal. In this situation, H will be -1. But if we have something like HCl, Cl is a nonmetal, H is going to be +1. Okay, so keep that in mind. Hydrogen can be +1 or -1, depending on what it's combined with. Okay, this is also a very important one. Fluorine, if you see fluorine, just assume it's -1. Okay, there are very few exceptions when fluorine is not -1. You'll rarely encounter those though, so it's a safe bet to know that fluorine is -1. Okay, and then lastly, halogens. Halogens are the elements in group 17, right? So we have group 17 where we have F, Cl, Br, I. Those guys are usually gonna be -1, but when they're with oxygen, they're gonna be positive. Okay, and we're almost done here. Okay, and then lastly, when you add up all the oxidation numbers in an atom, it has to equal whatever its charge is. So if we have a polyatomic ion like SO4 2-, when you add up all the oxidation numbers, they need to add up to -2. If you have something neutral like CH4, if you notice there's no charge, that means when you add up all the oxidation numbers, it has to be 0. Okay, so I know that was really annoying, and it kind of doesn't make sense right now, but make sure you guys have your screens on this this part of the workbook. We're gonna do some problems to finish up class, and that should help you guys understand what the heck oxidation numbers are and what we use them for, okay? So I know I'm sure there's a lot of questions, a little bit confusion right now, but it will get a little bit more understandable and easier once we go over a couple of the problems, okay? Okay, so let's go over the problems. Okay, so we're gonna be looking at 4.10 first, and then we'll move on. Okay, so what we're gonna do here is we have 6 different compounds. Let me zoom in actually a little bit more. We have 6 different compounds. And again, make sure you guys have your Chromebook screen open to the rules just so you guys can take a look at it. But we're going to be taking a look at, excuse me, 6 different compounds. And what we're going to be doing is we're going to try to find the oxidation number of sulfur. Just so you guys know, guys, if you guys are screwing around back there, please don't come to me for help later, okay? We're going over something important, and if you guys are going to be playing noises out of your phones and just kind of watching videos, I don't really want to help you guys out, okay? Make sure you're using your time wisely. Okay, so let's look at H2S. So take a look at your rules for oxidation numbers and look at hydrogen. What did we say the oxidation number for hydrogen is going to be? Let's go back to the rules. Okay, so if we look at this rule, right? Hydrogen. So hydrogen usually has an oxidation number of what? +1 with a nonmetal and -1 when it's bonded to a metal, okay? So if we go to H2S, is sulfur a metal or a nonmetal? Yes, sulfur is a nonmetal, right? Sulfur is a nonmetal. So if it's a nonmetal, what's the charge on each hydrogen gonna be? +1. So hydrogen is going to be +1 here, but how many hydrogens are there? 2. Okay, so we're going to have 2. So here, if we look at the molecule of H2S, it'll look something like this. It'll be H, H, and S. It looks like this. So each hydrogen is +1. If you notice, H2S has no charge, right? It's not positive or negative. So that means the charge has to equal to 0 at the oxidation numbers have to be 0 at the end. So if we have 2 hydrogens that are +1 each, +1, +1, what does sulfur's oxidation number have to be to balance it out? -2. There we go. So the answer to this problem is sulfur has an oxidation number of -2. Okay, so this isn't very difficult math. It's just finding the rules that we need and applying it to each element. That's what makes it difficult, I guess. Yes. Okay, so if we look at S8, okay, this is a molecule that's made out of only sulfur. Okay, so if something is made out of only sulfur, this is going to be its elemental form. Okay, if a molecule is made out of only that element, one type of element, that's its elemental form. So if S8 is sulfur's elemental form, what is going to be the oxidation number on sulfur here? 0, correct. Okay, and this is going to come from rule number 2, I think? 1, my bad. Okay.
We follow rule 2.
Appreciate that. Okay, so sulfur here, this molecule is only made out of sulfur, which means it's its elemental form, and so it has an oxidation number of 0. No, I just write my zeros like that. I'm weird. Okay, let's look at the next one, SCl2. Okay, so just a little hint. Let's look at the Cl first. Cl is what type of element? It's a halogen, yeah. Okay, because Cl is in group 17. Okay, so what did we say about halogens? What's the oxidation number for halogens? -1, except when they're combined with oxygen, right? But sulfur is obviously not oxygen. So that means chlorine here is going to be -1, and there's 2 of them, so it needs to be -1 again. Okay, now if you notice SCl, there's no charge, right? So if there's no charge, the oxidation numbers have to equal to 0. So what does sulfur have to be in order to balance out these oxidation numbers? +2, exactly. Okay. See, isn't this fun, guys? It's like a little game. Yeah, not fun at all, actually. Nah, dude, Stoic is the best. Stoic is the best. All right, guys, we'll do one more example, and then after that, I'll have you guys try the other 2. But let's try it out. So we have Na2SO3. Now, what we want to do first is you always want to try to start with the oxygens, okay? So we have 3 oxygens here. Now, if you take a look at the rules, what is oxygen's oxidation number usually? Yeah, -2. And there's 3 of them, right? So it's going to be -2, -2, -2. It's going to be -6, all the oxygens. Okay, now we could try to figure out Na, but we don't really have a good rule for sodium, right? So if you guys take a look at this molecule, does anyone notice anything special about it?
It's a salt.
It is a salt. So what does that mean about the anion? What is this? So this is a polyatomic ion. You might have noticed it. Maybe you couldn't find the words for it. So SO3 is a polyatomic ion. So if you guys take a look at the chart, what's the charge on SO3? Polyatomic ion, guys. Soul fight. Not -1. You guys are guessing. Yeah, it's -2. So if you guys take a look at your, I know this is annoying, but if you guys take a look at your oh yeah, it's right. Come on, guys. Yeah, SO3 is gonna be, maybe I put that there on purpose. That was part of my master plan, but I forgot. So SO3 is always gonna be 2-. Okay, so we don't even need to look at the sodiums here. We said polyatomics always have to be.
Good morning, students and teachers. Please excuse this interruption. We will be COVID screening in the auditorium during lunchtime today. If you receive an email regarding screening, please report to the auditorium. Screening will also be opened up to any staff that needs to screen. If you have questions, please contact the office. Thank you.
All right, anywho, sorry about that, guys. So we said earlier, if you guys take a look at rule number 4, that all the sum, if you add up all the oxidation numbers, it has to equal the charge, right? SO3 is always 2-. That means everything inside SO3 has to equal 2-. So if 3 oxygens are -6, what does sulfur need to be to get it to -2? Yeah, +4. So sulfur here is going to be +4. This is going to be the oxidation number. Okay. All right. Do you guys think you guys can solve SO4 2- and SO3 2- on your own? I'm gonna take that as a yes. So I'll give you guys a minute to try that out. Shouldn't be too bad. We actually just did the last one. maybe just another minute. Alrighty, guys. If you're still finishing up, feel free to finish up. But I'm gonna start going over it, so that we can maybe squeeze in one more example. Okay, so SO4 2-. What did we say about oxygen? What is oxygen's oxidation number usually? -2. So if there's 4 of them, what's the total? -8. Now the charge on the ion is -2. So that means when we add the oxidation numbers, it needs to end up to -2. So what does sulfur's oxidation number have to be to get it to -2? +6, exactly. So here, sulfur is going to have an oxidation number of +6. Okay, and then we actually just did this one. We said that oxygens are going to get us to -6. In order to get us to -2, sulfur needs to be +4. Okay, so those are going to be the oxidation numbers. Okay, so we're going to do one last example before we finish up for the day. I'm not going to go over everything in 4.11 just because there's so much, and I think that you guys can either try the problems at home, or I think you guys have a good handle on this. But let's try a couple of these out and then we'll get started, okay? So here it's asking us to find the oxidation state of the underlined element. So we're trying to find the oxidation state for phosphorus here. Now, if you notice, lucky for us, we have a bunch of oxygens. Oxygen's really easy. So if there's 5 oxygens, what's the oxidation state of all the oxygens combined? -10, right? Because it's 5 of them, and they're all -2 each. So -10. If you notice, P2OH has no charge. If it's no charge, everything has to equal to 0 at the end when you put them together. So what does the state oxidation number of phosphorus have to be in order to get to 0? +5, exactly, because there's 2 of them, right? So that means we need +5 and +5. That way they can cancel out the -10. Yeah, we're looking at them individually. So each phosphorus has to be +5. Okay, and again, it's because we have 2 phosphoruses, which are going to be 5 each, and then we have 5 oxygens, which are -2 each. So if we have 5 of them, that'll get us to -10. To balance it out, we need up 2 different +5s. Okay, one last one, and then we'll be done. Okay, so part B, NaH. Okay, we're looking for H. Okay, we actually need to use one of the rules to find this one. Okay, so if you guys take a look at the oxidation rules, which rule do you guys think we should use? Yeah, we're going to use rule 3, part B. Hydrogen is going to be +1 when it's bonded to a nonmetal and -1 when it's bonded to a metal. So sodium is a metal, so what's the oxidation number for hydrogen going to be? -1, exactly. Which means, what does the oxidation number for sodium have to be? +1, right? So that they can equal 0. And that's it. So I do encourage you guys to try out the rest of the problems on your own at home. You should also try the oxidation problems or oxidation reduction problems at home that are on your homework. I do want to mention to you guys, I am delaying the test. It was supposed to be this Friday, but for now I've pushed it back to next Tuesday, but I might push it back even further, okay? So let's kind of keep a thumb on that, but just keep in mind, we are delaying the test, so don't freak out and don't cram Thursday night because I've delayed the test from the original date, okay? It's at earliest, it's gonna be next week, okay? And I'll see you guys 2 more times before then at least. All right, so let me know if you guys have any questions. This will be on YouTube later. Smash the like button, subscribe, and if you want to, you can join the channel. I'm just kidding, I don't have that.